Okay, so continuing off where we were just looking at how we can see that around Sagittarius A star, we have a supermassive black hole. So check out those videos again if you want to watch those. So the other cool thing about our galaxy is how the galaxy is rotating. So the stars and the gas in our galaxy orbit in the same direction. They also have the same orbital speeds, which is pretty phenomenal. So this week we're going to do an activity looking at dark matter. So when you start this activity, I want you to start, when you start thinking about the galaxy, don't forget about Kepler's laws. So it's not unnatural to think that if there's a supermassive black hole at the center of our galaxy, and that you would imagine most of the mass in our galaxy lies at the center, that stars closer to the gravitational center would go faster, and stars further would move slower, just like Kepler's law told us from early on. But instead, what we see is that all the stars and all the gas rotate like a solid disk, going at the same speed. This is weird, okay? And so this tells us that there's something else going on in our galaxy. Oops, whoopsies. Okay, so looking at the star formation in our galaxy, the spiral arms are waves of star formation that spread out throughout the galactic disk. And we see a lot of star formation happening in these spiral arms, and not as much happening in the disk. So the spiral arms are moving as one unit through the disk. The stars are actually moving through all this gas and dust as well. And you might think that's because we're all gravitationally bound to that huge supermassive black hole in the center. That's really not the case. So the disk of stars that forms the major component of the Milky Way galaxy has its shape due to what, do you think? So what do you think keeps that shape? All right, it's that rotation combined with the collapse due to self-gravity. Okay, so self-gravity is all the material within the disk, within that bulge, coming together. So it's that rotation and the gravity amongst all the material in the disk, in those spiral arms. So the material in the Milky Way stays in orbit due to the combined gravitational force of all the matter within that object's orbit. So you could use the orbital motion of our sun to determine the mass of the galaxy within our own orbit. And now, because we see very few stars and virtually no gas or dust in the halo, we concluded that, you might not be surprised, that most of the galaxy's mass must not give off very much light, because we would think all of it would be in that plane of the mass of our plane in the disk of our galaxy. But instead, those calculations of how much mass should exist between our sun and the center is too big compared to what we visually see. So therefore, the extra mass, we must not be able to see at all. And that's what we call dark matter. Okay, so we find that most of the galaxy's mass consists of what we call invisible dark matter in the halo. About 90% of the mass of the galaxy is this dark matter. So we see this dark matter by its gravitational influence on the stars and how our Milky Way galaxy rotates. So what we think is that the dark matter is a spherical halo around the galaxy. Something like this. Okay, so the mass of our galaxy is estimated to be about 500 billion solar masses, which is way bigger than if we added up all the mass of all the visible light we can see. So there's something else out there, and that something else is this dark matter. So what is dark matter? We really don't know. Okay, that's one of the still greatest mysteries in astronomy, is we're not sure what dark matter means, what dark matter is. We know it has a lot of mass, and we know we can't see it. We've been trying to figure out what it could be. So take a moment here to pause the video, check out this video, and I'll put it in the lecture slides or in the module about explaining dark matter in 6 minutes. I think you'll really like it. Okay, in the next video, we'll talk about galaxies.